Hello friends, welcome to the second video for Fraunhofer Diffraction. In this video, as I have told you earlier, I will be doing the derivations for Fraunhofer Diffraction. Pay attention because this topic is the most important topic for the examination. So to derive the Fraunhofer Diffraction intensity and all, we first have to draw the ray diagram for Fraunhofer Diffraction. So let me draw the ray diagram first. So friends, I have drawn here the schematic diagram for Fraunhofer diffraction. So as previously we know, in Fraunhofer diffraction, a plane wavefront is incident on the narrow slit, that is this one, and each vibrating point in the plane of the slit becomes the source of secondary vibrations or secondary disturbances. So here, this is the slit. I have enlarged the view. This is the slit, and the slit width we have taken as D and divided into a large number of infinitesimal element strips. Large number of infinitesimal elemental strips of equal width, that is dy. So elemental strip width will be equal to dy. Taking the center of the slit as O, let this be the center of the slit. Let this be O as the origin of the coordinate system. So we have taken O here as the reference point, and we consider a small element dy at length dl or at length L, that is this of the wavefront. With coordinate 0, y. So here if we enlarge the view, we see this. Here is the L that we have considered here, and this is M. So this will be y sine theta, as this is y. You can see this distance is y, and let the distance OP, that is OP, equal to R, and LP equal to rho. So let this distance be rho, and the coordinates of P, let it be x0, y0. This is the x-axis and this one is the y-axis. So if we consider OM, that is only this distance, OM is from a right angle triangle, O, L and M, that I have drawn here for convenience of understanding. O, L and M forms a right angle triangle where this angle is 90 degree, this angle is 90 degree, this is y sine theta, this is y. So we can see, if we consider OM, the distance OM as equal to delta R, therefore we can see rho will be equal to R minus delta R, that is rho will be equal to R minus delta R. So by considering this, let's proceed further. So now, considering the previous diagram, let displacement at the point P, that is displacement due to the wavelets at slit O, it be Z0, where Z0 will be equal to A sine omega t, which implies that Z0 will be equal to A sine 2 pi by capital T, that is the value of omega, where t is the time period, into small t. So when the wavelet from with dy at L will reach at P, that is where this was the diagram and this was point P. So let when the width dy at L will reach at P, the amplitude will be Let me write it. When wavelet from with dy that is present at L will reach P, the amplitude will be A into dy. Hence, the displacement at P due to the elemental dy at any time t will be given by dz, that is dz then will be given by a dy, that is this value, into sine of 2 pi into small t by capital T minus rho by lambda. So remember this value. Now if d is the width, we already know that d is the width of the slit, then total disturbance, that is total disturbance that is at the point P, at the point P, the total disturbance due to the whole wavefront, we have to integrate it. So Z will be integration of dz, that is this value we have already written, from minus d by 2 to plus d by 2. Since the length of the slit we have considered it as d, that I have shown you in the previous diagram, so the half of it will be d by 2. Since we are considering here as O, we are considering this as a reference point, so the distance will be minus d by 2 to plus d by 2. So we are integrating to get the value of z here. So let us see what we finally get. Therefore, it will be equal to, here a is constant, we are taking out, integration from minus d by 2 to plus d by 2 of sine of 2 pi into small t by capital T minus rho by lambda dy, which will be equal to integration from minus d by 2 to plus d by 2 sine of 2 pi into small t by capital T minus, we are putting the value of rho here, that is r minus y sine theta, that we have already shown why it is y sine theta in the previous diagram, divided by lambda here for dy. Since, let me write the reasons why we have taken this. We have considered OM equal to delta R, and that is equal to y sine theta, we already know, and rho is equal to R minus delta R. So rho will be equal to R minus y sine theta. That's why we are getting this step. Now integrating further, we get that is equal to, cut, start, that is equal to a into integration from minus d by 2 to plus d by 2 of sine of 2 pi into t by capital T minus r by lambda plus we are separating this term, that is y sine theta, by lambda for d of y, that is equal to minus, now if we integrate this, we can see we will get a here, then lambda divided by 2 pi into sine of theta multiplied by, if we integrate this, we will get cos of 2 pi into t minus capital T minus r by lambda plus d sine theta by 2 lambda minus of cos 2 pi into small t by capital T minus r by lambda minus d sine theta by 2 lambda. We'll get this whole term. That will be equal to, if we subtract and formulate again, we'll get a lambda by 2 pi sine theta into, is multiplied by 2 sine 2 pi into small t by capital T minus r by lambda, that is this term, into sine of 2 pi multiplied by minus d sine of theta by 2 lambda. Again, equating this step, what we will getting? A lambda by, from here we will get pi sine theta into sine of, here will be pi d sine theta by lambda into sine of 2 pi into small t by capital T minus r by lambda, which again on equating we will get AD of, where A is multiplied to d of sine A by A, that will put the value, into sine of 2 pi multiplied by small t by capital T minus r by lambda, where we have A equal to pi d sine theta by lambda. So if we put the value of A here, we will get this. Again, we will see that we can write this as capital A theta into sine of 2 pi into small t by capital T minus r by lambda. So here we have concluded this term as A theta. Therefore, writing for our convenience, we have got A theta, that is capital A theta, equal to A d sine of A by A. So we can write this term as this equation. So we have got the resultant equation as capital A theta into sine of 2 pi into small t by capital T minus r by lambda. If we see this equation carefully, we see that this is also a harmonic motion, equation of a harmonic motion, or we can say SHM, that is simple harmonic motion. So we know that this is the amplitude of the vibration of the harmonic motion. And we also know that intensity is equal to the amplitude square, or the square of amplitude. Therefore, we can write I equal to a theta square, where the value of a theta that we have concluded before will be a into d into sine of a by a whole square. That will be equal to a square into d square into sine square a by a square. Therefore, we can write this term as I naught, that is, so we get the final formula as I is equal to I naught square into sine square a by a square. So this is the formula of intensity regarding Fraunhoffer diffraction process. We know that the intensity I will be maximum for zero deviation. Therefore, I max will be there at theta equal to 0. That is, after passing the slit or the lens, the deviation is 0. That is, the lens will not be there. That is, only the slit will be there. And after passing the slit, if the deviation is 0, then we can get the diffracted beam at maximum intensity on the screen. Now, let us determine the position for maxima and minima. First, we have to consider central maximum and central minimum. If this will be central maxima, then there cannot be another central minima. So it will be the secondary minima that we are going to consider here. So number 1, we have to take out the position for central maxima or central maximum position. So here we know that theta will be equal to 0, as I have already shown you in the schematic diagram. That is, alpha will also be 0, and we know limit alpha tends to 0 sine alpha by alpha, the value is equal to 1. Therefore, I is equal to I naught, that is the value of maximum intensity. That is equal to a square d square. So this will be the position for the maxima. So the central maxima will be obtained at theta equal to 0, that is at the point O dash in our schematic diagram case. Now let us further move on to the secondary minima. So now let us consider the secondary minima. Secondary minima will be seen at sine alpha equal to 0, which implies that alpha will be equal to n pi, we know from trigonometry, where the value of n is equal to plus minus 1, plus minus 2, plus minus 3. Or we can say that d of sine theta n is equal to n lambda. we can conclude this for the secondary minima. Since A is equal to pi d sine theta by lambda, we know from the previous derivation. So this is the condition for secondary minima. If this considerant is followed, then we will get the secondary minima case. Now let us come to point number 3, that is the secondary maxima. For secondary maxima, we know that there will be two of them. So sine alpha equal to plus 1 and sine alpha equal to minus 1. Let us combine these two cases. We will get alpha, the value of alpha equal to 2n plus minus 1 into pi by 2. Therefore, we can say that d of sine theta n will be equal to 2n plus minus 1 multiplied by lambda by 2. So this will be the condition for secondary maxima to occur. Now I will show you the graphical representation for the positions of secondary maxima and secondary minima, and also of the central maxima. So friends, as I already said before and derived the values of intensity for maximum and minimum values, this is the graph that comes in the exam. You just have to draw these portions of the graph. As you can see, this is the central maxima. That is only one. That is the highest value of intensity after deviation. And this is the secondary maxima. And this here is the secondary minima. So we can see we have two secondary minima, two secondary maxima, and the intensity goes on decreasing both the way. Here we have I naught and here we have I naught by 22. This graph is plotted by experimental considerations, and this where we have I naught by 62. Here is 0. We can show the phase, that is pi, 2 pi, 3 pi. Similarly in the opposite side, minus pi, minus 2 pi, minus 3 pi. If in examination it comes to draw the intensity distribution due to Fraunhoffer diffraction process, you only have to draw this portion and show the value of different intensities, that the intensities goes on decreasing due to the diffraction. So friends, in this video we have derived the position for central maximum and secondary maximum and also secondary minimum, and we have seen how the graph works or how the intensity get decreased from primary to secondary maximas and minimas. Thank you for this video, and in the further videos we will learn the derivation for width of the secondary maximum or minimum.